In this problem, we want to find the shape or the dimensions of a right circular cylinder of maximum volume which can be inscribed in a given sphere. Now, that may not even be straight off clear to you what's being asked, so let me draw a picture. So if we have a sphere, it's going to have some fixed radius k. So we've got, so this is the given sphere, and we know its radius is k. And we're going to inscribe a cylinder. So we're going to place a cylinder inside of the sphere, and we want to maximize it. So we're going to have to make it so it reaches the, touches the boundaries of the sphere. So here's our sphere. Let's put some variables on the dimensions of the sphere that we have control over. So we've got the radius r of the sphere, and then we have the height h. So let me write that. So h is the height of the cylinder, and r is the radius of the cylinder. Right, so those are the two variables we have, and we want to maximize volume. So volume is a function of r and h, and it's the area of the circle times the height, right? So it's going to be pi r squared h, and we want to maximize this volume. Right? We want to make it as big as possible. So that's the setup. And as we saw in the other two problems, though, we need some constraints. We need something that connects r and h. And at first blush, it might not be clear what that should be, but let's take a look. Let's add a line here, and this distance would be h over 2, and it makes a right triangle. So let me draw that over here. We've got a right triangle like this. This length here is k, the base of our triangle is r, and the height is h over 2. And that can give us a constraint, or does give us a constraint. So our constraint is that k squared has to be the same as r squared plus h over 2 squared. And since I recognize there's an r squared here and an r squared there, I'll go ahead and solve for r. Now there's a lot of variables. You may say, oh, I've just got a third variable. But remember, this is a fixed sphere. So k is radius of sphere, and it's fixed. I don't know what it is, but k is a constant. So that k is a constant, so I can solve for r squared. R squared is equal to k squared minus h squared over 4. And putting that into our function for volume, we can call this new function. We want to maximize, we want to make this function as big as possible. It's going to be f of h, right? That's my only variable is h, which is equal to pi times k squared minus h squared over 4, which if I multiply this out, or times h, sorry, times h. And if I multiply this out, this is going to be pi k squared h minus 1/4, got a pi up there, pi force h cubed. So this is a function we want to maximize. What's our constraint for h? Well, h can't be any taller than twice k, and it can't be less than 0. So 0 is going to be less than or equal to, actually it can't be equal, our height can't be 0 because then we'd have no volume, and it can't be any bigger than 2k. And I can't be equal to 2k because, again, if it was 2k, then I'd have no radius. So I don't have endpoints in this problem. So if I'm going to look for critical values, they're all going to be interior critical values. So now we know how to approach a problem like this. We're going to take the derivative, set it equal to 0, and solve. So we want 0 to be equal to f prime of h. And that's equal to, and don't get lost here, that k is a constant, just like pi is a constant. So when we take the derivative, h is our only variable. So this is equal to pi times k squared. And then when I take the derivative here, it'll be minus 3 pi over 4 h squared. And so this whole thing is equal to 0. So this tells me that 3 pi over 4 h squared has to be equal to pi k squared, which says that h squared has to be 4/3. So the pi, when I divide through, will cancel. So it'll be 4/3 k squared. So h would have to be plus or minus square root of 4/3 k. Okay, well, we can throw out the minus, right? Because the height in our problem can't be negative. And so we're left with root 4/3 k, which is definitely less than 2k. So we're in the domain. So our critical value is, we only have one of them. So our critical value is simply square root of 4/3 times k. Okay. Now, since we only have one critical value, we'll have to use, or we can use the second derivative test. So let's compute our second derivative. So f double prime of h. So this is a constant. So the derivative of that is 0. And so when I take the derivative here, I'll get a negative 3 pi over 2h. And evaluate it at this point. So f double prime of root 4/3 k is equal to negative 3 pi over 2 times the square root of 4/3 times k. And since k positive, this whole thing is negative. And if it's negative, this means that we have a max. Right? Because the second derivative test, we've got negative, therefore we have a max. And what are we asked for? Well, we're asked for the shape, or really the dimensions. And so I know what h is. H has to be root 4/3 times the radius of the sphere. And now let's solve for r. So solving for r, we have that r squared is equal to k squared minus h squared over 4. So we have that r squared. So putting this value, our h value in for h here, is going to be k squared minus 1/3 k squared, which is equal to 2/3 k squared. And so r has to be the square root of 2/3 times k. Therefore, writing out the final answer, we have that a right cylinder inscribed in a sphere of radius k will have maximum volume when the radius is root 2/3 k and the height is root 4/3 k.